this register to the output port, which is also controlled by the logic here. And the fourth timing path is in to out, where it is from the input port to the output port. It is also determined by the placement of the input port and output port in the design. ECOs should not affect the physical verification parameters, and ECOs are stage by stage process in static timing analysis to fix setup and hold time. So it is between the STA engineer and the physical design engineer who will work towards timing closure. So this will not affect the physical verification parameters. So timing to be met is 0 picosecond in both setup and hold time, unless we have proper waivers from the STA guide. Usually for setup and for hold time, they will have some waivers given by the STA person, but it is a rule for the physical design engineer to be to make sure that he meets timing. The next step is physical verification. Physical verification checks include DRC, LVS, design rule check, layout versus schematic, electrical rule check, and the resistance checks. So what are the three basic DRC checks? We check the width of the metal layer, spacing between metal layers, and via enclosures. DRCs are quite tricky to fix in low technology nodes, because in low technology nodes like 10 nanometer and so on, the distance between the source and drain is very close, and the spacing violations, all the there are more chances of shorts occurring in the floor plan and in the design. So DRCs are quite tricky in low technology nodes, and these checks should be run in parallel to avoid last minute surprises during tape out. Like we can check for DRC in the floor plan step, in placement step, because in Innovus we have options like verify DRC, verify geometry. So all this will give you instant results of your DRC and spacing violations, and you can fix them in each step of physical design. And this is LVS, which is a very important check in physical design between the physical design portion and the front-end team. So this GDS is from the physical design team, and this schematic is the circuit, which is now a transistor. So you have an extracted netlist from the GDS and a source netlist. This source netlist was used as an input for physical design. So we do a comparison and we check, we get an LVS report, and in this LVS report, we will check for shorts, opens, and to make sure that all the layouts for the IPs being used matches the schematic of the IPs. So we need to make sure that all the inputs given in LVS are the updated inputs, and it should make sure that all the pins in the IPs are the same in both GDS and schematic checks. The third step in physical verification is checking for antenna violations. So to fix this antenna violation, we add a diode near the gate. So this helps to fix antenna violations. Next is the logical equivalence check. This is to make sure that even though the design passes through different steps in physical design, the function still remains the same. So initially, once the front-end team gets the netlist, the RTL, they do the RTL modification, and they check whether it is still logically equivalent. And after synthesis, they check whether it is synthesized correctly by running this LEC check, and it will make sure that the function still remains the same. And then the synthesized gate level netlist is given as an input to the physical design team, and at the output, we have the place and route netlist. So a logic equivalence check is also applied there to make sure that even after clock tree synthesis, even after adding repeaters, buffers, and doing place and route, the function still remains the same. So this is a check being done at different stages in IC design flow to make sure that the function still remains the same throughout the IC design flow. So what are the softwares used in physical design? And also the VLSI field are Cadence, Synopsys, Mentographics, ANSYS. So Cadence is used to design integrated circuits and PCBs. Synopsys for design and verification, and also for timing analysis. We use a software from Synopsys, a tool called PrimeTime. And Mentographics is used for physical verification. And power analysis is done by a tool called ANSYS. So we do both static and dynamic power analysis using this tool. And what are the job roles in the semiconductor industry? We have design engineer roles for front-end, back-end design, FPGA, design for testability, analog mixed signal design engineers, RF design engineers, and IP design engineers. And when it comes to verification, we have front-end verification teams and engineers who run verification checks on the front-end output. For back-end verification, the back-end team itself takes care of it, and the physical design engineer is capable of doing the design and as well as the verification. And we have EDA tools validation engineers who validate the tools when a customer purchases a tool from an EDA company like Cadence. Each customer will have a validation team, and they will run validation checks with the EDA tools, and only then they will introduce it to the team. And we have IP verification engineers. We have application engineer roles, and this is mostly in the EDA companies like Cadence, Synopsys, Mentographics, where they have corporate application engineers who come down to customer sites and they do presentations to promote the tools. And we have field application engineers who work closely with the customers, and they come down to the customer site to fix bugs in the tool and to solve issues caused by the EDA tools. And we have manufacturing engineers who work in foundries as fab engineers, fab managers, tech support guys, clean room engineers who take care of the production of the chip. So what are the major recruiters in VLSI? We have ST Microelectronics, which is a French company, MediaTek, which is a Taiwanese company, Infineon, which is a German company, and NVIDIA, which is into graphic processors. We have TSMC, which is a major foundry tool, because most of the chips get manufactured at TSMC. And we have Qualcomm, which is more into 5G. And most of these companies, they have lots of design centers in India. And we have Intel, Xilinx, Texas Instruments, a very old US company. We have Broadcom, Micron, and at the bottom we have Cadence, Mentographics, and Synopsys. And these three are EDA tool companies, and they provide the tools for the companies above to design this IC and produce it. So with this, I would like to end my keynote lecture for today. And if you have any queries and clarifications, you can write to me, or you can visit my LinkedIn profile too. Thank you.
Thank you, sir. On behalf of our Electronics and Communication Department, I would like to spread my most sincere thanks to Engineer Samuel Jigme, sir, and also apologize for the unintentional delay. Thank you so much, sir, for adorning your necessary work and sharing with us graceful opinion. It was a great pleasure to hear you. Once again, thank you, sir.
Thank you, ma'am.
Also, I would like to say that participants kindly note that there will be 2 tracks running parallelly, that is track 6 and track 7. Kindly join your respective tracks by joining the assigned links you are provided with. Thank you.
Thank you.
Thank you, sir.
Thank you very much.
Thanks for the opportunity, and best wishes for the conference.
Thank you. Thank you. Thank you.
Thank you, sir.
Right.